Okay, welcome back everybody after the lunch break. I hope the lunch was healthy and within the reasonable amount of calories. So this afternoon we're going to spend the 3.5 hours talking about the following subject, which is the transportation. And the transportation in the NCEES, let me show you the beginning of the transportation section. It is on page 298. So the so starting on page 298, you will find the. We get some additional material here. So the on page 298. So welcome everybody. This is a transportation lecture for the FE7, and today is May 22nd, 2021, and this is Dr. Mansour again. So the transportation started on page 298. There is one section here they are referring to the industrial engineering section, which I will talk about it later on. But started here with the traffic signal timing, stopping side distance, the SSD, peak hour factor, and so on. So peak hour factor and vertical curves, okay, with all these equations on page 299. And if you look to the page 300, series of equations provided or they extracted from the AASHTO book, the 2011, by the way, they are using the AASHTO 2011, the older edition. The 6th edition is not the 7th edition. The 7th edition is the current one. This is the 7th edition, 2018. This is the AASHTO book. It's called A Policy on Geometric Design of Highways and Streets. It's a very important document. It's called the Green Book. But for some reason, they decided to use the old one. No problem. The same concept with some kind of modification of the equations. We have series of equations here we're going to talk about, which is a vertical curves, side distance related to curve length. We'll talk about all these fancy equations. After that, the horizontal curves on the same page, page 300. The horizontal circular curves with all these fancy equations also. And also some additional material related to horizontal curves, the super elevation, the spiral curves, and the HSO, the horizontal side offset. If you flip the page on page 302, they are talking about the HCM, the Highway Capacity Manual. The HCM is a very important document. This is the HCM. It is the 3 volumes. This is the Highway Capacity Manual. This is volume 1 and volume 2 and volume 3, 3 volumes. This is volume 3, interrupted flow, and volume 2, uninterrupted flow. So the highway capacity manual is one of the references that we use it heavily in transportation. So they extracted some information from there, very concise, by the way. They didn't really extract too much. And when I explain it also concise as much as I can. The highway capacity manual, and they are talking about the basic freeway segments. Okay, basic freeway segment or segments. Okay, so the 2000. I believe 2011 or 2000, no, 2018, sorry, 2018, okay, which is the 6th edition, yes, 6th edition. Much better, let's go with the edition. So they extracted these equations from there. We'll talk about all these equations, all this, until they went back to the Green Book, the 2011, the 6th edition, talking about traffic flow relationships. And after that, they talk about the trip generations and models like gravity model and logit models. After that, they move to another section, which is traffic safety equations. They picked this, by the way, they picked all these equations from a book by Garber and Hoyle, but they are using very, very old edition, the 4th edition, Garber and Hoyle, which is this one here. I used it when I was teaching way back in last course in New Mexico. Garber and Hoyle is called Traffic and Highway Engineering. Garber and Hoyle. This is the 4th edition. In fact, I used it way back when it was the 1st edition. This is the 1st edition. Okay, Garber and Hoyle. It's called the Traffic and Highway Engineering. They consider it one of the best books available in the market for highway traffic and highway engineering. Right now, they have the 5th edition and the updated 5th edition. They call it what? The modified, I think, modified 5th edition. So they pick some stuff from there. But the original of all this, by the way, it came from safety manual. Okay, so but they are referring to Garber and Hoyle, and also they are getting portion of it from the yellow manual. It's called HSM. It's called Highway Safety Manual. Highway Safety Manual. Manual. And the Highway Safety Manual, by the way, the HSM, is an AASHTO document. And the first time that the AASHTO, they decided to go with different color. Always AASHTO, they have a green box. This time they decided to go with what is known as the yellow manual, the Highway Safety Manual. Volume 1 and 2 and 3. It's 3 volumes, Highway Safety Manual, and we're going to talk about this. And finally, the last section of the transportation is talking about the highway pavement design. The highway pavement design, they picked it from AASHTO, also AASHTO Green Book of pavement design. Let me see if I have it handy here. Yes, here it is. This is design of pavement structure, AASHTO. So basically, the information in front of you, it is extracted from different sources and different books and different manuals, but they are making it so concise. Okay, and I will do all my best not to go beyond what is given because this is what they are expecting you to learn. So here it is. So this is chapter 13 from the AASHTO no, sorry, NCEES CBT, they are, okay, expecting, or you are expecting, or you will be expecting that between 9 to 14 questions, number of questions related to transportation engineering. They are talking about geometric design, streets and highways and intersections, and pavement system design, thickness, subgrade, drainage, rehabilitation, traffic capacity and flow theory, traffic control devices. Traffic control devices, normally we get it from something called MUTCD. MUTCD, Manual and Uniform Traffic Control Devices. This is also another reference. Also, it is a thick reference like this. Here it is. MUTCD, Manual and Uniform Traffic Control Devices. This is the edition that we are using in 2009. And finally, transportation planning, traffic forecast modeling, safety, and trip generation. So even the topics, few topics here, but the amount of equations and the information are really huge, and I will do all my best to keep you awake, number one, and to make the subject interesting. And all this was extracted from my famous transportation book. I have 3 transportation books. This is one of them, Transportation Module Reference Manual. This is the 3rd edition, and it is about, how many pages is that? 600 and something. Very thick book, 632 pages, a book I came up with, and I hope that it did help the PE, and I hope it will help you. So I extracted a lot of example problems, and we will solve as many problems as we can today. So let's start. Let us start. The first section in the NCEE is talking about traffic signal timing. So signalized intersections, the one we are using on a daily basis, it must be adjusted very well, and it should be designed very well to provide the best level of service with minimum delay and with minimum accidents, hopefully. So here are the equations they're providing. Y, which is yellow time, this is the length of the yellow interval, okay, they define is equal the T, which is the driver reaction time in seconds, plus V divided by 2A, plus or minus 64.4, which is 2G, in fact, times G. G, the uppercase, is grade. All these terms are defined for us. This is from the NCEE. So plus or minus uppercase G, this is the percent grade divided by 100, and the upgrade is positive and downgrade is negative, as all of you know. V, by the way, is the lowercase v. This is a vehicle approaching speed. It must be in feet per second. And this is, we're going to see it, feet per second, feet per second. And normally we take the mph, the mile per hour, and multiply it by 1.47 to get it feet per second. As we are going to see the 1.47, it will show up in many equations. And the 1.47, it came, by the way, from 5280 divided by 60 divided by 60, because this is how many feet per mile, and 60 minutes and 60 seconds. So this will give us, this will 5280 divided by 60 divided by 60 will give you in the neighborhood of this number here, which is 1.4667. So we round it to be 1.47, and we are going to see this equation. G is the grade, and the A, by the way, is called deceleration. Deceleration rate, this is feet per second square. Normally it's about 10 to 11.2, and it should give it to you. So this is the first equation. Nobody will ask you to memorize, and the reason they put a plus or minus here, because I said that the positive grade is positive. Positive grade is upgrade, and the negative grade is the down. So the second equation, R is equal W plus L divided by V. This is the lowercase r is called the length of red clearance interval to the nearest 1/10 of a second. When we have signalized intersections, and this is 522 to 1, and this transportation. This is FE. When you are at a signalized intersection, obviously the phases of the signal, so if it is green for these vehicles, it's green in this direction, obviously it was going to be red on the other direction. So if it is green here, such that the traffic, okay, in both directions, east-west, for example, if this is north, so the east-west traffic is going to be green. The other traffic will be red, waiting. When the green will go to yellow along this direction, the yellow basically they are telling the passengers or the vehicles in this direction, be ready because it's going to be red. Okay. When this is red, this is still red also. They call it all red. And they are using the letter R for the clearance time. Because if this Mr. Mansour, he's driving here and it is yellow, and he catch the last yellow second, so he's driving fast, so they need to ensure that I will clear this intersection before the other direction turn green. This for safety. So all red, and they're using, some book they call it AR or red, but the NCAA they're using R, lowercase r, and the R we're going to see it a lot by the way, but this is how they decided. So the R is the length of the clearance of red clearance interval, and normally so it's equal, WW is the width by the way of the intersection from curb to curb. L is the length of the vehicle, because they need to ensure that the entire body of the car has been already outside the intersection. So they need, so this is L, the length of the vehicle. Normally we use 19 feet for passenger car, and you should give it to you normally 19 to 20 feet. Divided by V, also the V is a feet per second, And the third equation is G sub P. G sub P is the minimum green time for pedestrian. If I am here right now, I am waiting on this side here, okay, and there is a crosswalk here, and I need to cross this intersection, so it should be green for me, okay? So how much time, the green time is needed for pedestrian to cross? So they came up with this equation. There are two equations, in fact, but they provide only one, which is 3.2. 3.2, by the way, this is the starting time, because if I'm here and it turning walk, I'm not going to jump. It will take some time. They found that on the average 3.2 seconds is the startup time, plus L over S sub P. L is the length, by the way, the length of the crosswalk, and S sub B, this is the average speed for the pedestrian speed. Normally we use 3.5 feet per second. They found that the average based on the age, and they did the studies, and they came up with the 3.5 as an average value. Sometimes they give it to you as 4 feet per second, but whatever the default value, and so a plus, okay, 0.27 in pedestrian. In pedestrian, by the way, this is the number of the pedestrian waiting here. How many people are waiting if there is a business here, if there is a business or a school here or commercial facility here, or so obviously the number of the pedestrian waiting to cross the street will be large, and in this case we need to know the end pedestrian, how many pedestrians are waiting here, so we can adjust the green time. So those are the equations, and as I said before, these equations are nobody will ask you to develop them, nobody will ask you to memorize them, but we need to know the components or the parameters of these equations and how to use them. And again, I'm emphasizing units. Units are very, very important in every subject. And as I mentioned this morning, we don't like to lose lose the exam because of the units. So the first equation, which is this equation here, it is 2G, by the way, but they report it as 64.4, where G is the 32.4 feet per second. So this equation came from, by the way, Traffic Engineering Handbook. There's another book, don't worry about it. And this is the ORED, as I told you, but some book they are using AR or just as. This is a clearance time for signalized intersections or intersection, and we defined this before. And the third one, which is the minimum green time for pedestrian at signalized intersection, and this is based on the HCM, the Highway Capacity Manual 2016, and this is the equation. The G sub P is equal to 3.2, which is the startup time, L over SB plus this. And this is an illustration here showing you the pedestrian crossing, okay, time at intersection. So if we are here right now, or we're waiting here, and we have the crosswalk width, which is the width of the crosswalk, and we have a length, which is L from curb to curb, and we are using this equation to determine how much is the minimum. Always, by the way, codes provide minimum green time for pedestrian, and this is in seconds, okay? So always I refer to the FE reference handbook 10.0, and as I told you that in the future, probably I will write the page number, but for the time being, I needed to write after me, okay, the page number, at least you can go back. And so this is a page 298. So this is here, page 298. Okay, at least you can go and compare the equations if there is any typo or mistake or an error. Sometimes, by the way, I write the equation. For example, this is the same equation we just saw. I give you the reference, the HCM, the Highway Capacity Manual, just in case if you like to read more. And this is, by the way, for the when the width of the crosswalk is 10 feet, okay, or less. So they provide you with one equation, but there are two equations, in fact. I include a lot of problems. In fact, this section has many problems, except two, as I told you before lunch. I was trying to get them, but I was not able to finish them. I need to double check. So I did not include them. They are blank in this book, and I will be glad to send it to you when I review them. Problem 13.1. A signalized intersection is located in an urban area. The average vehicle approach speed is 35 miles per hour. The width of the intersection is 24 feet for all approaches. The average vehicle length is 20 feet. The deceleration rate, which is A, is given. The length of the yellow interval is 4 seconds. The grade of the road is given -4%. The driver reaction time is most nearly. What's the driver reaction time? If we go back again to the equation, by the way, the equation, this T, what is T? T is the driver reaction time, okay? Driver reaction time, because the driver is waiting and he putting the foot on the brake. The moment, okay, that react, how many seconds does it take that? And we're going to see the driver reaction or the the driver reaction time. We're going to see it in another location. It could be 2.2 seconds or 2.5 seconds. It depends from one location to another. So this is the, we need to change first of all the 35 miles per hour to feet per second. As I told you, it is 5280 feet per 1 mile, and 1 hour has 3600 seconds. So basically it is a 1.47, I mentioned here it is. So if you take 35 miles per hour and you multiply it by 1.47 directly, but here it is a 1.47, is coming from the conversion, and this is, okay. This is the equation. Here it is. So we substitute for everything except we are solving for T. So in this case, T is equal to 1.65 seconds. So we rounded to be 1.7 seconds. So the answer is B as in boy. Okay. And again, I will double check to make sure that they are matching. This answer should match whatever the answer given should match here, because sometimes I change these. So this is one equation. So here he is not asking you to calculate the yellow time. No, the yellow time is given and he is asking for T. So we need to resolve for the or solve for the driver reaction time, which it came out to be 1.65 seconds. Okay, it's about 2.2 as an average. 2. Some books they are using 2.5. Standard is 2.5, by the way, in the green book. But whatever numbers we ended with. Okay, units again here. Again, problem number 2. He said that the following information are given. The grade is given 1%. The average vehicle approach speed is 44 feet per second. So this is ready to go. And the width of the intersection curb to curb, this is W. And the driver reaction time, okay, is 1 second. And the deceleration rate, which is A, 10 feet per second square. And the speed limit on the approach is 60 feet per second. And the vehicle length is 18 feet. Here, as you can see, there is a lot of information are given for us, but he said the red clearance time, which is R. The R, or the all red, where all the signals in all directions will be red to clear the intersection from those who enter the intersection at the last second of the yellow, okay, phase. So, or the yellow. Okay, so this is the R, so it is 50, which is given, plus the 18 divided by, so it is 1.55 seconds. So in this case, we selected the answer. It seems to me I rearranged these things. So it is this correct? Let me double check here. So it is 50, okay, feet enter 18 plus, and 44 divided, so it is 1.55. So I will pick the answer B as in boy. So this could be a typo here because I probably change it. So it is 1.55, unless I missed something here. Let me make sure that the width is W is 50, L is given to be 18 feet, and the V, which is the approach, okay, V is the vehicle approach is 40 feet. 44 feet per second. So everything, it looks good. So it's just probably I rearrange the answers here. So the answer B. If you flip the page, you will find that problem 3. I gave you this intersection here, and the pedestrian demand is 0.9 pedestrian per cycle, and assume the average pedestrian is 4 feet per second, is not 3.5. So this is the equation. Okay. This is the equation. So 3.2, this is the pedestrian startup time, by the way. I explain it here from where they come up with the 3.2, because the passenger or the, pedestrian will take some time until they start to move. So this is the equation. So L is given to be 76. How is 76? You are adding all this. This is L. Okay. This is the length. Okay. Let us keep it, okay, as L. Here I put as L sub D, probably I will keep it as L to given, okay, to match exactly. This is the original equation, but I will move the D, L sub D. But basically, so if you add this 11, 11, and 6 here, and 12, 12, 12, 12, if you add this, this is L. This is L. This is the crosswalk that the driver, okay, the length of the crosswalk, okay. Also, there is another definition for it. I don't like you to, and I will call this is just only L. So if you plug it into this equation, you will find that the time, which is again, I will call it G sub B, which is the same. They call it G sub B instead of the T. Okay, so is equal 22.4, and the answer C is the one is selected here. So this is what I need you to be aware of. So this is a typical example for the minimum green time for pedestrian, and again I will change it to make it okay exactly to match G sub B. Okay, and if you look to the second problem, problem number 4, you will find that if the number of the pedestrian arriving at the intersection here increased from 0.9 in the previous problem to 8, okay, and the crosswalk width is still 10 feet, we have only one equation, so this is the equation, and I will call it just L. So basically, the 3.2, there's still 76 is the length divided by 3.5, and the number of the pedestrian has been increased, so you'll find 27.07 seconds. So the number of seconds for the green time, instead of 22.4, okay, increased to 27.07. This is will allow, okay, the pedestrian, okay, to walk from one side of the street to the other side, and because of the number has been increased, we need to give them more time, and this is what's happening here, and you will find that the 27 seconds is the best answer. Normally, by the way, all the equations, by the way, they give us some kind of guideline for rounding. And if you go back again to the first page of this, so they said that, for example, R, the length of red clearance nearest 1/10 of a second. So if rounding is recommended, normally here it is, the yellow interval to the nearest 1/10 of a second. So normally they give us what is the rounding accepted, or the normal rounding. Okay, so the second section is talking about the stopping side distance, and again this from the NCEES, and this is on page the 298. So this is page 298 of the NCEES 10.0. Here there are two equations, one for the stopping side distance, which is SSD. Okay, the one I talked about it before more than once, that there is a similarity between this abbreviation and the saturated and surface dry, is 1.47 VT. The 1.47, by the way, for the conversion, and V is the speed in this case, but it's MPH. So they include the 1.47 to take care of the conversion from MPH to feet per second, so already built in. T is the driver reaction time in seconds, and this is normally 2.5 seconds, plus V square, which is the design speed, and the theory A over 32.2. This is G, by the way, this is a gravity acceleration. A is called deceleration rate. The deceleration rate feet per second square. Normally we use 11.2 feet per second square. This is the standard per ash to 11.2, but it should be given to you in the problem statement, by the way. Since it's not mentioned here, this is exact language given, unless I missed something here. No, this is not given. Okay, and obviously the grade is the same. This is called stopping side distance. What is the stopping side distance, by the way? I explain it here is the minimum distance required to come to a complete stop when you see an object. So side distance, okay, is how far the driver can see, okay, before the line of sight is blocked with a hill crest or an obstacle and so on. So the side distance is a continuous length, okay, of highway ahead that is visible to the driver. So the minimum distance is called stopping side distance. I am driving on the freeway or the street. By the way, the stopping side distance is applicable to all roads. Okay, stopping side distance, it should be available for all roads and streets. Okay, this is the minimum distance that is required to come to a complete stop before I hit an object. So I'm driving and there is a mattress here. Okay, or okay, driving and I saw a mattress here, okay, or a tire or anything object on the road. I should come to a complete stop before I hit this SSD. So I should be able to see, and you are going to see the illustration right now, because the height of the iDrivers, they decided to be 3.5 feet. And the object, they decided to be, this is 2 feet, which is the height of the rear bumper of a car. If there is a car on the road and it's a broken car, or so they decided to 2 feet. Some agencies, they are using 6 inches, by the way, half a foot. But we're going to stick with the AASHTO. This is AASHTO. In addition to the stopping side distance, they are going to also, or they ask us or ask you to know ISD. ISD is called intersection side distance. Okay, intersection side distance. ISD is called intersection side distance. ISD. Okay, which is sometimes we call it corner, by the way. So the ISD, this we use it only at the intersections only. But for the stopping side distance, use on multi-lane highways and 2-lane and any highway or any street or any facility, any transportation facility, it must be designed to provide the minimum stopping side distance. This is intersection. There are other 2, by the way, we cover them in the transportation, but they are not included in this. It's called passing side distance, is not required for you, and the decision side distance. We cover them for transportation, but I include them here just to let you know that there are some other side distances. Something is called passing side distance. We only apply to 2-lane roads. And decision side distance, this is at the decision points like off-ramps, branch connections, and so on. So we are not going to cover these 2. Just to let you know, for just to give you a feeling about the relationship between these 4. These are the 4 type side distances. Okay, for any given speed, like 50 miles per hour, I picked 50 miles per hour. The passing side distance, for example, is 900 feet. The decision side distance is 465. The varies, by the way. The decision for maneuver A and for maneuver E is larger, and the stopping side distance is 425. So 425 is the stopping side distance, which is the smallest among them. So this passing decision side distance, we have 5 of them. We have A, B, C, D, E, and finally the stopping. So I need you to know that the stopping side distance is the smallest one, by the way, smallest one for any given speed. The stopping side distance, which is the time required or the distance required to come to a complete stop. This is this is an illustration to show you what is the stopping side distance. So this is the 2 feet. This is the object. This is the object on the freeway or the street, and this is a passenger car, and they are using 3.5 feet. And there is one statement at the end. Why they select a passenger car? We call it B, by the way. B stands for passenger car. Passenger car. Because the trucks, they have advantage. They are higher. And they said that we are going to base the stopping side distance. So this is the stopping side distance. Okay. So this is if a straight, if there's tangent. This is called in tangent section. Tangent. What about if you are in a curve? If you are in a this is a crest vertical curve. This, we are going to see types of vertical curve, sag and the crest. This is a crest. This is a crest vertical curve, crest. Okay, so you'll find that also for the curves that they have G1 and G2, we're going to see the grades. Okay, we need to ensure that while you are driving on a curve, you should be able to see ahead of you, okay, if there is any broken car or any object on the road. So this is called the stopping side distance, and this is for all roads and highways. We should have it. The other one, which we will not discuss it here, is the passing side distance. Passing side distance will apply it only on the 2-lane highways, 1 lane in each direction. Here it is, 1 lane in each direction. You are driving, and there is a vehicle here is slow. Okay, so you need to speed up to take over the other lane and come back before the other car coming on the opposite direction. So there are 2 phases, phase 1 and phase 2, or first phase and second phase. But this is just to show you. So this is called passing side distance, passing side distance. And And we have a lot of issues with the passing side distance because you need to ensure that the car coming from the opposite side or the opposite direction will not really in conflict with you. You have to go back again to your lane before the other car coming. Okay, and all of us, we experience that. This is just an illustration. So this is a PE exam. I'm using this illustration for the PE. And here it is. This is a slow car and you need to pass it. Just go and pass it safely. So you need to pass the PE exam. You have to study right now. I can modify this. I will say that the FE exam. So you need to study to pass this. Okay. So the stopping side distance, okay, side distance is the distance along a highway through which the object, okay, an object of a specified height is continuously visible to the driver. This depends on the what? Depends on the driver height and the object height and any lateral position that may block, okay, or obstruct. So the stopping side distance consists of two components. Okay, the stopping side distance consists in the distance traveled during the brake reaction, because the moment I see an object, what I will do, I will take my foot from the brake, okay, and from the gas, sorry, and I put it on the brake. It's called reaction time. And the moment I hit the brake, the car will travel a distance. So the distance to brake the vehicle to stop. So they took this, and this is what you are going to see. The first one here, the 1.47 VT, this is the reaction time. Reaction, or the distance it traveled, reaction during the reaction time. Because the moment I took my foot from the gas to put it on the brake, it will take some time. So the car is traveling. And after that, this is the braking time, a braking distance, sorry, a braking distance, or the distance that will, okay, that the car will brake, B-R-A-K-E, braking distance, okay. So the two parts of this equation is given. This is another illustration here, that this is the line of sight, this is the driver, and this is the height of the driver, which we use at 3.5, and the object is 2 feet, by the way. They decided to go with the object of 2 feet. So the line of sight must be clear such that you should be able to see the object. So you will take the action, and in this case, so the stopping side distance on level or flat roads. This is the general equation. If the grade is not given to you, we ignore this, we take it as 0. There is no such thing as called 0 grade. As I told you, there is a minimum grade, the 0.3%, plus or minus, and the 0.5%. If you remember, 0.5% minimum grade, this is for drainage purposes, plus or minus. But for the stopping side distance, we call this is level road. So this is level, okay, or flat grade. So use the general equation. If the G is not given to you, the grade, in this case, we ignore this portion, which is this one here, which is G. So for what is the stopping side distance for given? The stopping side distance for 60 miles per hour, level road, here it is, assuming the deceleration rate 11.2, and the perception reaction time, which is T, 2.5 seconds. So it is 1.47, this is 60, this is MPH. Don't convert it again, because the 1.47 is the conversion factor from MPS to feet per second. And this is T, perception reaction time, 60 squared divided by 30. This is the deceleration rate, and 32.2. So this is 565.5 feet. In this case, we round it to be, and there are some tables given in the ASH2 book. Don't worry about it. Normally we round this to be 560, 570. We round it to 570, the design, but this is a calculated one. So the SSD, the stopping side distance. Here I'm mentioning also something about the stopping side distance and the grade. What is the grade is, I explain it to you. Okay, grade and side slopes and all these things. If you look to the following page, you will find a couple problems. One is talking about the slope of a segment of a 2-lane highway expressed of the vertical angle. We said the vertical angle, it could be positive, it could be negative. So if a road like this, and they told you this vertical angle is a plus 3 degrees and 30 minutes. So what is the grade in this case? G. And in this case, the grade is going to be plus. So if the angle is given, the vertical angle is given, okay, so right now we can take this is the rise and this is run. Okay. Go with 100 feet because the grade is going to be percentage. So to make it easy for you normally, so rise over run is equal what? Is equal tangent. The angle rise over run is equal tangent theta, or tangent V in this case, the vertical tangent theta, called theta. So theta is given. Can I get the rise? So the rise is equal the 100 times the tangent is giving you the 6.12% and is a plus. Be careful, okay? Because the angle is positive. This vertical angle, as we learned from surveying this morning, the vertical angle could be plus or minus. The following problem is talking about the braking distance. Here, this is a braking distance only. We said that the Stubbing side distance consists of two components. Be careful what he is asking. This is the distance it traveled during the reaction time, and this is the distance traveled when I hit the brake. So this is a braking distance, reaction distance. He's not asking for the SSD. The SSD is the total. Okay, the Stubbing side distance is the total of the two components of, say, this is the braking distance. Okay, they call it, by the way, this will be the code, to code. This is the braking distance, here it is. So basically the second part of this, I needed to be aware of that because sometimes they can ask you only for one portion. So it is V squared, this here, everything. I use the grid, by the way, is coming from the previous problem. The 6.12, this one here. So this is 6.12%, and I use a plus because here a plus or minus. So this here, as you enter it in your calculator, is going to be 0.0612. So you have to divide by 100. Make sense? So in summary, the stopping side distance, SSD, consists of the distance traveled during the brake reaction time, plus the distance to brake the vehicle to come to a complete stop. Also, I needed to be aware, as can be seen from the above equation, that the stopping side distance needed for upgrades are shorter. This way, if I have G is positive, which is upgrade, so and this could be plus, so you divide it by a larger number, so the distance is going to get smaller. And this is expected because I'm going uphill. So I need a shorter distance. While I'm getting, if I have negative grade, so this is negative, so I'm subtracting, so the denominator is getting smaller, so the stopping side distance will go up. Okay, are shorter than the one on level roads, and those downgrade are longer. The downgrade are longer for sure because I'm subtracting this. So I needed to understand that because it could be a conceptual question asking which one is larger and why and all these things. Okay, and be careful, this only the braking distance is not the entire stopping side distance. And finally, I added another problem, 13-8. Okay, assuming the perception reaction time is 2.5 seconds, the D cell is given, and the stopping side distance for this for 60 miles per hour and 6 downgrade. Here it is, downgrade. So in this case, the G is going to be what? Negative. And here is asking for the stopping side distance. So the two components of the stopping side distance taken into consideration, the G is negative and 6%, and you'll find it is 637, which is the answer C. So this matching this and this matching this. Okay. If you look to the same problem, okay, which is problem number 5. Okay. Problem number 5, the flat, this is 60 mile per hour, 11.2 and 2.5 seconds. Similar to this. 60 mile per hour, 11.2 for the deceleration rate, and the perception reaction time 2.5 seconds. I need here 637. But for a level road, I need only 565. You see that? Okay. And if you calculate, by the way, let me just for the sake of discussion, if you look to problem 13.7, where the grade is positive 6.12%, so this is the braking distance. So if you would like to get the SSD for this one here, it is 1.47, and I have 60 mile per hour. Let's make it 60 mile per hour, because he put 50 here, just to compare it with the other 60, times 2.5 seconds. Plus what I calculated here, which is, you can say that this is 60 square. Let's do it 60 square, because it will be a little bit different. So it is 60, so it is 0.612 enter, and 11.2 enter, okay, 32.2 divided. And this is 30 times inverse, and 60 seconds square times. So it is 293.4. 293.4. So if you add this, so 1.47 enter, 60 times, 2.5 times, and you add 293.4 plus, this will give you 513 only, 513.9 feet. So now we have 3 distances I need you to be aware of. This for the 6.12% upgrade, positive, 513. For a flat, I need 565. So basically you have flat, let me write it here, at least you can see. So for the same speed, for V is equal 60 mph, and for T, perception reaction time 2.5 seconds, and the deceleration rate 11.2 feet per second square. These are the given information. For level road or flat, we get a distance of 500. For the stopping side distance, SSD is 565.5 feet. For upgrade, a plus G, and this is plus 6.12%. What did we get? We got 513.9 feet. Check my math, please, just in case. Okay. This is also the stopping side distance, SSD. And finally, for downgrade, which is negative G is 6.12%. Okay, this is negative. We're getting a distance of the larger number, which is 637.4 feet, 42 feet. So you can see the effect of the grade. This is a flat or level road where G is not considered at all. This is upgrade. I need a shorter distance because I'm going uphill. Okay, this is going down. This is the largest among the 3, which is expected. So I needed to be aware of that. This is all this, the SSD, by the way. This is the stopping side distance. So we need to be aware of all these things. Okay, make sense? And when you receive my notes, please calculate these things one more time and make sure that you really understand all these things, because it could be a target for a question. So stopping side distance SSD. Okay. there is one comment here. I got it from the Green Book, the Ash to Green Book. If you remember, the driver eye height is 3.5 feet. I know we have SUVs right nowadays, but they found, okay, we are looking for a passenger car because an SUV is higher, so that he can see farther or okay beyond a passenger car. So they consider the 3.5 feet as an average, and the average height of an object is okay. It is 2 feet, like okay, like the height of the rear bumper of a car or a tire or something. Here it is, the iDriver, and this is a standard, by the way. Okay. The comment they made on the Green Book, the Ash to Book, they said that the recommended stopping side distance given in the previous equations are based on the passenger car, okay, operation, and do not explicitly consider the truck drivers or the truck operation. Trucks as a whole, especially the larger one and the heavier units, need longer stopping side distance for sure for any given speed than the passenger car. However, there is one factor that tends to balance this additional braking length for trucks, that the truck drivers can see substantially farther beyond the vertical side distance obstruction, okay, because of the higher position of the seat. So this is a justification of the Ash to. This is the Ash to, by the way, the Green Book. They are saying that there is no need to consider the truck because the truck has advantage that it is, in fact, it's 7.8 feet, by the way. We are going to see the height of the, except only one location, the 7.6. For trucks, they con 7.6 feet instead of 3.5. And the 8 feet, there is only one location, and we're going to see the height of the iDriver in a truck cabin later on in another section. So this is called the stopping side distance. The following section is talking about the intersection side distance, ISD. The ISD in the Ash to Book, they having, by the way, many cases. They have intersection side distance. It's very complicated. They have case A and case B, and case C, and case D, and case E, and case F, and the case G. They add G this year. And the B, by the way, they have B1 and B2 and B3. And they have C1 and C2 here. So many cases and many stipulations, and we cover this in depth in my transportation book, and also attending with me today transportation from the PE, they know exactly what I'm talking about at an intersection here, like this intersection here. So what they did for the FE, they took only one case. They took only case A, okay? They only the easiest, okay, the case A, and they modified a little bit with some other cases. So they are saying that this is an intersection. This is an intersection, okay? You can say it's A, but more inclined to B. Let me put it that way, okay? And right now, this car is coming in this direction, and this car is coming in this direction. Let's just assume we have a major street and a minor street. So assume this is a major. So this is a major one. And this is a minor. Normally we're assuming that the minor street, he has to come to a complete stop. So while he is stopping here, he should be able to see the cars coming in all directions, okay? And the same story here, on the minor street has to come to a complete stop, no but a stop sign, okay? So they are saying that the driver here and the driver here must look, and they must be able to see the cars. And they came what is known as the triangular, okay, or the triangle of vision, okay, sighted triangle. And there are equations. Nobody will ask you to derive these equations, which is basically the side triangle. The side triangle. And there are two side triangles. One is called departure and one is called approach. Approach side triangle and the departure side triangles. And this is for the intersection side triangles. Okay, so basically what you see on the hatch here, if I'm driving here and there is a car coming this way, I should be able to see this car. This is my line of sight. This, it must be clear for me. This is why they don't allow any building or any trees to be planted here in order to clear this. The side distance is very, very important. So, and the same story here. If I am here and the car is coming this way, I saw the clear this. This for the approach. For the departure, okay, here you are coming to a complete stop and you start to move. You should be able to see this car from this side. And you're supposed to see this car from the other side. In order to make a left turn or through or right turn, we have, as I told you, many cases. I'm not going to talk about that. The equation that we are going to see, or you are going to see on the exam, one equation. This equation here. The intersection side distance is equal 1.47. V major, okay, the major street, assuming that the minor street is going to come to a complete stop, times T sub G. T sub G is called the gap, time gap. And the time gap, we have different scenarios, by the way, but he didn't explain it. We have for passenger cars, for trucks, and slow grades has effect and number of lanes and so on. But he would like to make your life easy, or for the sake of the FE, the T sub G will be given to you. But for the PE exam, no. We ask them, or they ask them to calculate the T sub G. So it is only one equation, okay, for the intersection side distance. So a passenger car is turning left into a two-lane undivided major road with a stop control on the minor. If I translate this into English like this, here it is. So this is a major street or the major road, and this is a minor road. The minor road is controlled by stop sign. Okay, here it is. There's a stop control on the minor road. So there's a stop sign here and there's a stop sign here. This hexagonal, okay, shape, do you remember the hexagonal shape? The hex, okay, the stop sign. So the driver on the minor road here and the driver, they have to come to a complete stop. The major, no, the major will not stop. So he's saying that the driver here, he would like is a two-lane undivided. This is undivided. There is no median. Divided, we're going to talk about divided highways and undivided highways later on when we talk about LOS, level of service. But basically, this driver here is waiting and he would like to make a left turn. So they are saying that if I know the V major, which you should be given, V major, and we are using 7.5 seconds as a T sub G or TG, that means that the distance from here to here, the distance, by the way, is measured along, this is the distance we're talking about. This is the dimension B as in boy, which is the length. I need to see how much the car should be away from the intersection. Okay, the leg B. Okay, so this will give me how much distance in order this driver to turn left safely before they hit this car and or this car. So this is called intersection side distance. Is 1.47. Again, this is 60 or 50 miles per hour. We use it as is with no change because already the 1.47 included in the equation, and T sub G is given, and this is the intersection side distance for this. This is the time gap for minor road vehicle to enter the major road. It's called intersection side distance. Okay, so the following topic, we are going to see it later on in one of the applications, but they decided to put it here as early. It's called peak hour factor, BHF. This is on page 298 also. So page 298. Peak hour factor. In the highway capacity manual, we're going to see it. Here it is in the HCM. I provide you also the equations from the HCM. If you'd like to read more about this, I provided you with the reference. So this is the section that's given in the NCEES. So the peak hour factor is defined as the hourly volume, which is they are using V for the hourly volume, vehicle per hours, how many vehicles enter the intersection, divided by the hourly flow rate, but they multiply here by 4. Let me make sure that, okay, the hourly flow rate, which is basically 4 times V15. They are using the 15-minute as a criteria in the traffic analysis. So it is the peak 15-minute volume and multiplied by 4 because there are 4 quarters in the hour. Here I repeat the same thing, but before that I provide you with the peak hour factor, the hourly volume during the maximum volume hour of the day divided by peak 15-minute flow rate within that hour is a measure of a traffic demand fluctuation within the hour. We need to see the fluctuation of the traffic flow within the peak hour. Always the peak. Okay, we pick the peak hour only. Okay, so the peak hour factor is used to convert the hourly volume into 15-minute flow rate for the HCM, for the highway capacity manual, and some typical values, by the way, typical values between 0.8 to 0.95, higher values in urban and congested facilities, and lower values obviously for rural and uncongested facilities. In order to calculate the peak hour factor, this is an example. So we start at 4 o'clock p.m. or from 4 to 4:15, I have 850. So the following are the traffic count at intersection for a 2-lane highway in an urban area. So from 4 to 4:15, they found 815 vehicles enter the intersection. Okay, between 4:15 and 4:30, this in all directions, by the way, it is 950, and 4:30 to 1,000. So this, it must be an hour. Okay. An hour is defined by the code, by the way. It's the 4 consecutive core 15 minutes. I cannot jump because sometimes they give you the count, okay, 2 hours, and I will show you how to do that. So basically they are saying that let us sum this. So this is the total volume within that hour. Here it is. Divided by 4, because there are 4 15 minutes in an hour, times the peak. Which one is the peak? Is 1,000. So I pick the peak 15 minutes within the peak hour. So this will give you a number 0.8875. So probably 0.89 is the best answer. This is how we calculate the peak hour factor, which you are going to see it in the another equation when we'll talk about LOS. LOS is the level of service. Level of service. Level of service. Okay, we're going to see this later on. Okay, now the fun started. But I looked to your eyes, it seems to me, I don't know if my impression or to make sure that you are really, I looked to your eyes, it seems to me your eyes a little bit, not 45 degrees. Oh my God, how I know that? I don't know that. I don't see your eyes from here, by the way. Don't worry. It's just joking with you. Okay, try to keep you awake as much as I can. What about, okay, normally in the afternoon, I give couple breaks because I'm sure the calories or the circular burger or the square burger, whatever you decided, or whatever you had for lunch. So let us take one is admitting the guilt. He's saying he get. How did he come at 1,000 in the last? No, it's given. The 1,000 is given in the count. I didn't get 1,000 from here. It is 1,000. So the traffic volume between 4:30 and 4:45. This is a peak hour. This is a peak 15 minutes. So the 1,000 is here, my friend. Here it is. Okay. So I'm adding this plus this plus this plus this, which is the 4 quarters divided by 4 times the peak 15-minute volume. The peak is 1,000. Okay. So our friend admit that his eyes about 15 degrees only. Oh my God. So it is by far, you are, let's take 10 minutes break. Right now is about 10:15. So 10, not 10, my God. Dr. Mansour, wait a second. 10, 2:15. And we are going to meet again at 2:25. Okay. So try to get some fresh air. And as I always recommend, air without corona, please. We don't like to have any corona, okay, because we need everybody to stay healthy, okay? So let us take a short break and come back. Thank you. Welcome back, everybody, after this short break. This is one of the references that mentioned in the NCEES, Manual and Uniform Traffic Control Devices. This is the Federal Highway Administration, FHWA document. One chapter is talking about signalized intersections or signals in general. If you remember, I told you I need your eyes to be open 45 degrees. Why did I select 45 degrees? When they design signals and the driver is waiting here, okay, 10 feet away from the stop bar, this is where the driver's eye, he should have a cone. It's called cone of vision. This cone of vision, they measured the cone of vision for many drivers and different age and so on, and they found that the angle must be 40 degrees. So they put the signal such that it should be within the cone of vision of the drivers, the mast arm and the signal, so they should be visible to the driver within 40 degrees. So I'm a little bit conservative, so instead of asking the 40 degrees as recommended by the MUTCD, which is a cone of vision, at least you can see exactly the screen in front of you. So I'm asking 45 degrees. So a little bit conservative. This is how the 45 degrees came into play, okay? Just if you ask, why did I select the 45 degrees, the angle, okay? So our friend, he said that, so I need your eyes to be at least 45 degrees, please, okay? Because 50 degrees, no, 15, he told me 15. Okay, 15 is not acceptable at all. Okay, welcome back. Vertical curves. Vertical curves, there are many calculators available in the market that they have already software or they already built in programs. If you have one of these calculators, or if you decided to write your own program or programs, you should know how to use it before you go to the exam. But for the sake of the exam, you don't have to have this kind of calculator, because the NCEES, they have a calculator policy, and I need you to stick with the calculator policy because they might ask you to leave if you are carrying or you are having a calculator is not within the calculator policy. So in the NCEES, this is on page 299. So this is page 299, page 299. Vertical curves. Vertical curves, we are looking to the facility as a side view. Side view. You're looking from the side, how the highway or the streets is going up and down from the side view. Horizontal is a plan view, the one is coming after that. So there are different types of vertical curves. And you will find that I provided 4 tables. You are going to see them. The classifications of the vertical curves. It could be symmetrical or asymmetrical or unsymmetrical. It could be sag or crest. And in the AASHTO, they came up with 4 types. You are going to see it shortly. But basically, a vertical curve. Why we need vertical curves, by the way? Because topography or the terrain, if you have a road, you need to build the road in a mountain area. Okay, this is a mountain. Somebody may say, oh, wait a second, it's very easy, Dr. Mansour. Why need a vertical curve? I need to, you can build the road like this and build it like this. Oh my God. So Mr. Mansour is driving and going up here and stuck here. Oh my God. We cannot do that. We need to provide a vertical curve. A vertical curve, a smooth transition between 2 grades, G1 and G2. Lowercase or uppercase. Here, the AASHTO they are using, or the NCAA, sorry, they are using lowercase. Okay? But the AASHTO they are using uppercase, for example. But it does not make any difference for you if this is G1 and this is G2. I need you to know that G1, uppercase or lowercase, always associated with the beginning of the vertical curve. BVC, what is BVC? This is the point of vertical curvature or the beginning of the vertical curve. This also sometimes we call it beginning of the vertical curve, BVC. The BVT, this is the point of vertical tangency, or the EVC, end of the vertical curve. Here it is. BVT is a point which is the end of the vertical. So any vertical curve has a beginning and has end. Okay. So, and the vertical curve is the one is connecting these 2 points. This is a curve. And the curve is measured horizontally, by the way. L is measured horizontally. It's not like the circular curves. So the L, you take this station, minus this station will give you L. So beginning and end, like the FE. FE exam has a beginning and end. You started studying and you will end, okay, or it will end by receiving congratulations from the NCAA. Yes, let's do this as soon as possible. This, call it back tangent. And the back tangent always associated with the beginning of the curve. Forward tangent, always associated with the end of the curve. Okay? And we have some other points. This is BVI, point of vertical intersection. This tangent and this tangent are intersecting here. BVI. If this BVI is at L/2, means halfway between the beginning and the end, we call it a symmetrical vertical curve. And this is what you are going to see on the exam. So symmetrical, we are not talking about unsymmetrical. Symmetrical vertical curves has nothing to do with the G1 and G2, by the way. G1 and G2 not necessarily to be the same. Okay? But in order to say that this is a symmetrical vertical curve, the BVI, point of vertical intersection, here it is, point of vertical, or sometimes we call it vertex, V. Some books, they call it V. Okay? L is the length. There is E, letter E, and letter Y, and X, and A. A, by the way, uppercase A, which is this one here. This is the algebraic difference in grade, and we take the absolute value. It is G2 minus G1, and we take the absolute value. We don't take the sign. It's called the algebraic difference between the 2 grades. Okay? So this is A. What about E? E is not the modulus of elasticity. You remember we use modulus. E is the tangent offset at the point of vertical intersection. Offset, let me It's called tangent offset. So vertical curves, if it is a sag or a crest, it does not make any difference. So we have a tangent, back tangent, and we have the vertical curve, and we have the forward tangent. If you extend this tangent to this tangent here, they are going to intersect at the BVI. This is the beginning of the vertical curve, and this is the end of the vertical curve. Or this also, it is a BVC or BVT. And this is L. L is measured horizontally, is not along the curve. This is a vertical curve. Vertical curve, I need you to know, is a parabolic curve. It's not a circular curve. Parabolic. A parabola, we're going to see the equation shortly. Okay? They call this distance here E, and this distance here is Y. This is called offset. Y is called offset. So Y at the difference in elevation between a point on the vertical curve and a point along the tangent, they call it offset, or we call it offset Y. But one specific offset, they call it E. This is at the vertex, at the point of vertical intersection. What else? There is a datum, a reference, and after that, this is the beginning of the vertical curve. This is the Y, the elevation. So the tangent elevation is equal the Y BVC, which is the elevation, plus G1X. Okay? I need you to know that X measured from the beginning of the vertical curve. So the reference for the X is here, by the way. This is very important. This is the reference. So the X is between 0 and L. X here is 0. X here is L over 2 if it's a symmetrical vertical curve, and the X all the way to the end is equal L. So I need you to know that X measured from the beginning of the vertical curve, please. Okay? Or the other equation is the BVI, okay, plus G2, which is the second, times X minus L over 2. Because this is a symmetrical vertical curve, as I told you. L over 2, it came from that the vertex, or the BVI, it is halfway between the beginning and the end of the vertical curve. Curve elevation. I need to get the elevation along the curve itself. This is the tangent. Is equal this equation. This is the parabolic equation. So this is Y at any distance X is equal, which is a curve elevation, is equal the Y of the BVC, plus G1X, plus AX square. This is the equation for a parabola. As we know from calculus, parabolic curve or the parabola is second order. Tangent offset, which is Y, this Y here, is equal AX square. And A is equal A over 2L, or A, as you know, G2 minus G1. The E, which is the offset at the vertex, is given by this equation. R, it does have a name, very important. R is called the rate of a gradient change per station, by the way. Here it is R. Okay? R is the rate, which is, R, by the way, is G2 minus G1 divided by L. I believe it's given somewhere here. Yeah, here it is. And the R, it could be positive, it could be negative, by the way. Positive or negative, as we're going to see in the following page. K is very important. We use it in transportation. K is called the rate of vertical curvature. XM. XM is the horizontal distance from BVC to a point on the curve. In fact, the XM, I prefer, this is supposed to be, I believe this is a typo. This is the XM and this is X. Okay, I was thinking to switch them, and here it is to verify that. Yeah, XM is a maximum and minimum. The X is a general one. This is a typo I need. Okay, so I will put XM here, and they put just X. Okay, let me put a note here, at least I can. Here it is, at least I can correct that. Because we do have something that's called high and low, or minimum and maximum. High and low points, especially for drainage or for bridges. Y, already we know define what is Y is, and V is the design speed, which we are going to see. So a lot of variables. The letter A, by the way, small a, is called parabola constant, which is AX squared. Nobody will ask you to memorize equations. Nobody will ask you to derive equations, but we need to know how to use them, especially there are too many. And during the exam, you have a very minimum amount of time. If you flip the page, but let me grab a question from one of you. Probably I missed something here, or he would like to add something. That's correct. We use the highest count of 15 minutes. That's correct. The PHF is equal to the total volume in 1 hour divided by 4 times the highest 15 minute. Yes. Yes. Okay. And this is the equation is written based on that. Why we are using vertical curves, already I told you about the topography or the terrain. Why we are using parabolic curves? There are 2 reasons, by the way. The R, which is the rate of change per station, is constant, so the drivers will not feel bumps up and down. No, they smooth the transition or smooth driving as you drive on a vertical curve. Okay, so this, and it is easy for computation. Vertical curves could be either symmetrical, and this is what you are going to see, by the way. Symmetrical. Symmetrical means that this BVI, the point of vertical intersection, or simply vertex, it is halfway between the beginning and the end. This is the beginning of the vertical curve, and this is the end of the vertical curve. This here, L over 2, and this is L over 2. But asymmetrical vertex is not located at the half distance between the beginning and the end. We are not going to cover this. This is like compound curves. It takes double the time almost, and you don't have time to do that, so they decided to have only symmetrical vertical curves. So by default, I need you to assume this is the default. So the default is the symmetrical vertical curve, default. Vertical curves could be either sag, like this, okay, or crest, like the one given in the NCAAS. So this is a vertex, and this is a vertex. And this is G1, and this is G2. And this is G1, and this is G2. And this is the beginning of the vertical curve, and this is the end of the vertical curve. And this is L. This grade up is positive, like stock market. Down, negative. This is down, negative, and this is up, is positive. This is why you'll find that the R here for the sag vertical curves you will find that R is G2 minus G1 divided by L. But G2 is positive, minus minus, so this is why always R is positive here. I need you to know that. R is positive for sag, and R is negative for crest, always. Here it is, G2 minus G1. G2 is negative, minus plus will give you negative, and I need you to check that. The R, which is the rate of gradient change per station. And also I need you to be aware of this fact also, that the G2 is greater than G1. G2 is positive, greater than this. This one here is the opposite. AASHTO, they came up with the classification, by the way. They call it 1, 2, 3, 4. We're going to see it shortly, just for your knowledge. Okay, so this is a crest and sag vertical curves. So this is the E, and this is the vertex, point of vertical intersection, and this is the beginning, and this is the end. L is measured horizontally. This is symmetrical. Why? Because this is L over 2. So L over 2 and L over 2 is the vertex in the middle. Okay. We do have one high point, by the way. This is the XM. Let me put it that way, by the way. XM. They call it XM in the book. Probably I will change this also to make it XM. This is the, I use uppercase here or boldface, but XM is good. At least you can match, or we can match the NCWES. This is the distance from the beginning of the curve to the high or low point. And we have only one high and one low point for any given curve. Because mathematically, we're going to take the first derivative dy by dx and equate it to 0, as we remember from calculus, and we will see that like in math also. So only one high point and one low point for any given curve. Because here, this is where we put the di, the drainage, because when it rains, the water comes here. I need to get to collect the water here. For the high, if there is a bridge like this, and there is a truck, I don't like the truck to hit the bridge. So I need to know what is the highest point. So we provide a clearance, and we're going to see vertical clearance shortly. AASHTO, which is a green book, the one I showed you, okay? This is based on the 7th edition there, but still the same in the 6th edition. A crest vertical curves, they have type 1 and type 2. The reason I included that, because you might, here this is the standard one. This is a plus G1, and this is minus G2.